Hello, we are Group 8 and in this video we will present you the experimental and computational characterization of a shell and tube heat exchanger. Heat exchangers are devices that transfer the thermal energy from a fluid to another, however, these fluids are not in contact. In shell and tube heat exchangers, the heat transfer increases as one of the fluid moves inside the tubes, while the other moves through the shell. There are two types of classification according to the flow arrangement, co-current and countercurrent flow. The exchange of heat occurs due to two types of mechanism of heat transfer, which are convection and conduction. This video consists in showing and analyzing the results of the behavior of the temperature, the flows of each fluid, the thermophysical properties, and the global convection transfer coefficient in a shell and tube heat exchanger, using the computational tool CFD for the computational results and the experimental data in order to compare them. Materials and methods. The experimental setup was a HT33 shell and tube heat exchanger that could operate in either co-current or countercurrent. A temperature between 45 and 55 centigrades was maintained for the inlet. Experimental methods. Based on these experimental results, the coefficient was calculated by means of three different calculation methods. The first was LMTD, which was defined as the logarithmic mean between the temperature differentials of each fluid and each end of a heat exchanger, as shown in equation 1. In this method, delta T1 and delta T2 change according to the type of operation. Equations 2 and 3 are for countercurrent operation, and equations 4 and 5 are for co-current operation. To obtain the heat flow, equation 6 was used. The second and third method was Kern and Bell-Delaware. These methods only differ in the calculation of H, which means coefficient of heat transfer by convection. The equations of these methods are equations 7 and 8. Both methods use the same equations to calculate U and the shell heat transfer coefficient, which are equations 9 and 10. Finally, to obtain the pressure drop on the shell, equation 11 was used. These equations are very important to determine if the heat exchanger is working in well conditions. CFD methods. The fundamental equations to be solved numerically by CFD are the conservation equation of momentum and energy. Also, for the fluid, polynomial density was assumed because the density depends on the temperature and this changes throughout the system. In addition, steady state was assumed for the system. In terms of internal flows, the model chosen was K omega turbulence because it predicts very well close to walls. To generate the mesh, we used four models. The first one was the surface we measure. It generated an initial surface to the heat exchanger. The second one was the polyhedral measure that was used to generate polyhedral shaped cells in the volume of the steel and the hot and cold water. We chose this model because it generates less and more accurate cells than other volume models. The third one was the prism layer measure. This model considers the profiles formed in the liquid-solid interfaces by creating prismatic cell layers next to the solid boundaries. Finally, we use the embedded thin measure because it generates a prismatic mesh in the thin geometries. Also, we evaluated the Y plus parameter with the all and plus wall treatment. This parameter indicates that a mesh is good for the simulation when it has a value between 0 and 30. Table 1 shows the number of cells in the generated mesh. The total number of cells were 701,753, getting a final number of cells near the recommended. Figure 3 shows that there are some cells with poor quality, but the most important parts, that are the prismatic layers, are well defined for most of the heat exchanger. The values of the Y plus parameter in our simulation are between 0 and 14.5 with an average of 3.77. With the higher values for the tubes, that indicates that the mesh is adequate. It is necessary to consider that it was impossible to generate prismatic layers inside the tubes, so the interfaces were not well defined and therefore the flow inside the tubes did not have a realistic behavior. These are the temperature profiles for a parallel and countercurrent flow with a hot fluid temperature inlet of 50 centigrades. The temperature outlet is very similar in both cases. The increase of the cold fluid temperature is bigger in the zones with the deflectors. This figure shows the pressure profile for a parallel flow considering the gravity. It shows the pressure drop inside the system for both the cold and the hot fluid. For the fluid inside the tubes, the pressure drops as the fluid gets colder. On the other hand, when the temperature of the cooled fluid increases, also does the pressure. These results are expected because of the existing relation between these two physical properties. Velocity profile. This animation shows the velocity profile for the exchanger in co-current flow. This one shows the velocity profile of a countercurrent flow. In both animations, the deflectors cause a loss of velocity and create turbulence in the shell. The fluid inside the tubes has a constant velocity, but there is a difference at the entrance due to the expansion between the system inlet and the volume that is filled before the tubes. The obtained results for the heat transfer coefficient by each method are presented in this table. It shows that the difference among the LMTD method for the experimental and simulation is between 0.3 and 20%. This difference is not high, acknowledging that the simulation does not consider energy losses with the environment. Consequently, the heat transfer coefficients tend to be smaller for the simulation. The assumptions made for each method can also affect the final value of the heat transfer coefficient. For instance, the current method considers co-current flow to determine the equivalent diameter. Thus, there is an alteration in the counter-current flow calculations, which can explain why its heat transfer coefficients are lower than the co-current ones. Furthermore, the current method is a simplified method that puts aside the cross-flow and baffle window flow in the shell, generating deviations in the calculated heat transfer coefficients. In tables 3, 4, and 5, the principal values obtained by each method are shown. These values include the Reynolds number, the Prandtl number, the convection coefficient, the Nusselt number, and the pressure drop. Tables 3 and 4 show that for both methods there is a laminar float behavior in the shell, while in the tubes the fluid tends to be in transition to become turbulent for the countercurrent configuration. In the tubes there is a small deviation of the Prandtl number, which may be due to greater heat diffusion and less diffusion of the moment amount. The heat transfer by convection is height. Nevertheless, it does not imply that there is no height conduction transfer. In addition, the flow of the shell being closer to the environment presents losses because the system is not isolated. The calculations indicate that the characterized heat exchanger satisfies the pressure drop requirement and it is operating in an optimal condition for this parameter. Nevertheless, there can be deviations in the calculation zone due to the cross-flow assumptions to determine GS, which is used in the pressure drop calculation. Conclusions. Deflectors increase the temperature exchange. The simulations and experimental results were consistent. The calculated parameters were deviated due to the assumptions made for each calculation method. The lack of prismatic layers inside the tubes affected the flow configuration and therefore the simulation results. The difference between the LMTD heat transfer coefficient for the experimental setup and the simulation is due to losses that are not being included.